So what we're going to study today is nuclear magnetic resonance spectroscopy. I know a lot of you have intentions of going into the medical field. You may be more familiar with something that utilizes this concept and this technology called MRI, magnetic resonance imaging. Okay, so that essentially uses nuclear magnetic resonance spectroscopy, but then generates an image that can give you diagnostic information. So if you never take another organic chemistry course, you still have that to kind of cling to for application purposes. All right. So it revolves around the idea that nuclei are positively charged. So first of all, I want to make a point to say this is weird in chemistry that we're talking about the nuclei. That's a physics thing, right? But this is the way in which this technique works is we don't care so much about the electrons and the bonds that we're breaking or the bonds that we're forming. We care about the actual protons and the neutrons that are in the nuclei because overall the nucleus is positively charged. And I won't spoil it if you haven't taken physics 2 yet, but anything that's positively charged, it generates a magnetic field and is also impacted or interacts with an external magnetic field. The magnetic force is something you talk about in physics 2, so I won't get into it. I'll let you take that course to learn more about that. But if you apply an external magnetic field, it will impact the energy states of that positively charged nucleus, right? So if you don't have that external magnetic field, all of the magnetic fields generated by the nucleus are kind of randomly aligned, as you can see in that figure A. So the magnetic rotation of the nuclei is random in the absence of a magnetic field. However, if you apply a strong external magnetic field, so in the presence of a strong magnet, those nuclei will align with or against that external magnetic field. And we can cause the energy levels of those nuclei to jump if we subject them to radio frequencies. But the thing is, just like everything else at the subatomic level, the energy levels are quantized. And you can match those energy gaps in the radio frequency range of the electromagnetic spectrum. Okay. So when exposed to a radio frequency that matches the quantized energy gap, the nuclei absorb energy and jump to a higher energy state. And this is called resonance. Okay, so this is why we call this NMR, or nuclear magnetic resonance spectroscopy, because what we are detecting are those absorbances of those radio frequency energy gaps. But that radio frequency that does get absorbed, it depends on a few things. Two of them we're just mentioning, don't really care about too much today, but the third one is what we'll focus on. Okay, so the two that are less important for our purposes today are the strength of that external magnetic field, but also the identity of the nucleus. So this is one thing I will point out, but again, we won't focus on it today, is that NMR is a particularly powerful analytical technique because it is capable of analyzing lots of different element types. You just have to have a nucleus with an odd number of nucleons in it, okay, an odd number of that sum of neutrons and protons. So things like a hydrogen 1, that's an odd number. Carbon 13, phosphorus 31, and there's others. But as I said, today we're going to focus on this. So the electronic environment of the nucleus does impact those radio frequencies that are absorbed or emitted, okay? The other name for that would be shielding, also known as shielding. So electronic environment of the nucleus, also known as shielding. And the reason why it's called shielding is because, you know, those electrons are also charged particles. And as I mentioned in physics 2, you learned that anytime a charged particle is in motion, it generates a magnetic field. And so that magnetic field generated by the electron cloud is going to interact with the external magnetic field. So this is an opposing magnetic field produced by the electron surrounding the nuclei to counteract the effects of the external magnetic field. Okay, and once again, this is similar to what you were shown in the pre-lab video, so I won't go over it with much detail. Oops, but notice that this right here is your sample tube. Okay, so remember from the video that what you do is you dissolve your sample that you want to analyze in a deuterated solvent. Okay, and what we mean by deuterated is that all of the hydrogens in the solvent have been replaced with deuteriums. And remember that deuterium is hydrogen, but instead of just being H1, it's H2 because it has one proton and one neutron. So we give it a special name. It's called deuterium. So all of the hydrogen atoms in the solvent have been replaced with deuterium. And so that way it just doesn't interfere with the H1 spectrum, because you would imagine you have billions and billions of times of H1 atoms in your solvent compared to your sample. And so you wouldn't get any meaningful data unless you replaced all those solvent hydrogens with a deuterium. Okay, so that's what's going on in that sample tube. And this right here is the external magnet. So you put you subject it to a strong external magnet, and then the green line right here is just that radio frequency generator. So that's how we cause the absorbances, and then the blue is just the detector, okay? And that the computer does the work, and then it generates the signal, which shows up as a spectrum. Okay, so let's talk a little bit about the chart that's used in NMR. There's some vocabulary here that we need to learn. So first of all, it's on a scale on the x-axis, which has units of parts per million, ppm. Now, the axis that's shown right here is a sort of a abbreviated axis for hydrogen, for when you're analyzing H1. But it depends. The numeric values depend on what nucleus you're looking at, and you'll see that in an example in just a minute. But the higher numbers on the chart are what we call downfield or deshielded. Okay, so the higher numbers have several terms associated with it. We call it downfield, or we call it low field. But the other thing that's important to know is that those are the signals that are from deshielded hydrogens. Now, what we mean by deshield is that their electron cloud, the electron cloud around that hydrogen, has been kind of pulled away from the hydrogen because there's an electron withdrawing functional group nearby or an electronegative atom nearby. So because of that, it kind of pulls those electrons away from the hydrogen, which were shielding that hydrogen's nucleus. So therefore, we say it's deshielded. But the counterintuitive thing here is that, it's called low field or downfield, but it's the higher numbers on the chart. Now, contrast that with the other side, the right side of the chart. We call that upfield or high field. And again, it's counterintuitive because these are the low numbers. They're not high numbers, they're low numbers, 0 and 1 and 2. Okay, but again, this is the area of the chart where all the hydrogens are pretty much shielded by their electron cloud. You don't have anything nearby to withdraw the electron cloud like an electronegative atom or an electron withdrawing functional group. So the other thing I'll point out here is this TMS, this peak right here at 0. That's that black line you see. That's a peak that will show up in your proton NMR spectrum. But this compound right here, TMS, is tetramethylsilane, and it happens to generate a signal right at 0. And so we use it as a reference marker. Okay, so here's just a couple example NMR spectra. The top one is for the hydrogen, the proton, okay, and then the lower one is for carbon. So let me just point out a couple things. So as you can see, we've got some color coding here. The green hydrogens, the CH3 right here, those hydrogens are generating this green peak right here in the proton NMR spectrum. So this pink signal is generated by these pink color-coded hydrogens, and notice they are further downfield. They are more deshielded, and the reason why is because those hydrogens have an electronegative atom, this oxygen, nearby. So they are slightly deshielded, and so they are further downfield than the hydrogens generating that green peak. Okay, they don't have the oxygen as close. All right. So one other thing to point out, and this is the only thing we're going to say about carbon-13 NMR, because you notice that we run this sample, you run the proton NMR spectrum, and then you could also run the carbon-13 spectrum. So notice two things about it. First of all, the scale is different. Instead of going from 0 to 10, it goes from 0 to 200. So again, that scale, that x-axis depends on what nucleus you're analyzing. And the other thing is, notice that it's a little bit more noisy. So this for the proton NMR, it looks like a flat line. But for the carbon-13 NMR, it's very noisy. It's jagged, right? So the reason why is because remember that over 99% of the carbons are carbon-12, which is not sensitive to NMR. But carbon-13, because it has an odd number of nucleons in its nucleus, is sensitive to NMR. But because it's such a small percentage of carbon, you have to do more scans, and even when you do a lot of scans, it takes longer. By the way, the proton NMR you can get done in a matter of minutes. The carbon-13 NMR takes longer, like an hour. But even after that, you still get some noise in the baseline. Okay, so as I said, that's really all I'm going to point out about carbon-13 NMR today. If you take organic 2, you'll talk some more about that. Okay, now I want to mention the 3 important things that we get from NMR. And again, from now on, we're going to focus on proton NMR. And then we'll talk in more detail about each one. So the first thing that's important information we get from proton NMR is this information we call chemical shift. The reason why it's important is because it helps us identify functional groups in that compound and other structural features. Okay, next, we can get the peak integration And what that does is that identifies the number of each type of hydrogen. So it's kind of quantitative. So it can tell us, is that peak generated by one hydrogen, two hydrogens, three hydrogens, nine hydrogens? So that's what peak integration will tell us. It gives us a quantity of hydrogens that generate the peak in the NMR spectrum. And then finally, peak splitting. And this one's weird, but it's very powerful because the number of peaks that show up can tell us the number of hydrogens on the neighboring carbon. And that may seem a little strange right now, but we'll give you some more concrete examples in just a few minutes, okay? So peak splitting identifies the number of neighboring hydrogens. Okay, so first of all, we'll focus on the chemical shift. So as I said, the chemical shift is important because the position on the chart, well, yeah, I guess, well, first of all, what is it? It's the position on the chart, and it has units of parts per million, often given with the symbol of that lowercase Greek letter delta. And as we said before, we already talked about this vocabulary. The left area of the chart, we call that downfield. And what makes it unique is that those hydrogens in that region are less shielding, or they experience less shielding due to nearby electron withdrawing groups. For example, highly electronegative atoms like oxygen, as we saw earlier. Okay, so downfield is less shielding. Okay, and then the right side of the chart is called upfield. And there's just more shielding of the protons in that region because there's just a lack of withdrawing groups. There's a lack of electronegative atoms or lack of electron withdrawing groups like nitro groups or anything with a pi bond in it, like a carbonyl. Those are considered electron withdrawing groups. So the upfield, there's just a lack of that in the structure. Okay, and that's something else that I already mentioned that we can just put in our notes now. That compound tetramethylsilane is used as the reference marker. Pretty much every sample, when you run an NMR, you spike it with a half of a drop, just a teeny tiny amount. And what's useful about it is it gives us a nice, strong single peak right at 0 parts per million. Tetramethylsilane. Okay, so again, the importance of the chemical shifts is that they are characteristic of the functional groups and other structural features. Now, what do I mean by that? Well, if it's a hydrogen that's bound to an sp3 carbon, a saturated sp3 hybridized carbon, those are going to absorb and they're going to give us a signal upfield. Okay, so hydrogens that are connected to a tetrahedral carbon, we expect to see upfield. Now, it starts to shift downfield a little bit if those hydrogens are connected to an sp2 hybridized carbon. Okay, so protons bound to sp2 hybridized carbons absorb at lower fields. And also, protons that are bound to, will absorb at lower fields if there is an electronegative element nearby or another type of electron withdrawing group. So protons bonded to electronegative atoms absorb at lower fields, and this includes protons bound to carbons adjacent to electronegative atoms. So what I mean by that is, let me just draw something on the screen here. You can add to your notes if you want. Okay, so what we're talking about is, let's say that there's an oxygen and it's connected to a carbon, okay, that's got hydrogens on it. So these hydrogens, the signal generated by these hydrogens will be shifted downfield, even though they're not directly connected to the electronegative atom, but they're connected to an atom that's adjacent to an electronegative atom. Okay, so we see this both with hydrogens that are connected to an electronegative atom, like oxygen, a hydroxyl group on an alcohol, for example, or we could see it on from hydrogens connected to a carbon that are adjacent to an electronegative atom. Okay, so again, the chemical shift just gives us some structural information. So if we see signals, for example, that are in this range from 6.5 to 8, those are most likely generated, that signal is most likely generated by hydrogens that are on a benzene ring or some other aromatic ring. Okay, and as I mentioned earlier, if we see signals in this region from 0 to 1.5, what that means is those are hydrogens that are probably connected to just, saturated carbons, sp3 hybridized carbons. And again, that gets shifted downfield if you throw in some sort of electron withdrawing groups, like if it's an allylic hydrogen, which is, it's near this pi bond, this carbon double bond. If it's near a halogen, or in this case, if it's a vanillic hydrogen, so it's directly connected to this carbon-carbon double bond, that kind of pulls electron density out of that carbon-hydrogen bond, so away from the hydrogen, de-shielding it. But the point being is that each of these regions in the spectrum are characteristic of certain functional groups. With integration, all these look like real sharp, straight lines, right? But if we zoom in, we would see that it really is kind of like a curve, something like that. And so we could actually use, if you learn this in Calc 2, actually an integral. So we integrate, we just figure out the area that's underneath that curve. Okay, so that's what integration is. All these peaks are really, they're curves like this if we zoomed in. And the integration is the area underneath that curve. And so, for example, the vertical part, if you take the difference between the base and the top of this integral line right here, that's what this black line is meant to represent. So that right there represents the area underneath that pink curve. And this right here, the difference between that base and the top of that integral line represents the area underneath that green peak right there. Okay, so the difference, the height of that integral line, okay, is the area underneath the peak that it corresponds to. And so you can see over here that it's just relative. Okay, so let's look at the green color coded hydrogens first. So we've got a total of 9 of those. There's 3, 3, 3. All those are equivalent. Those hydrogens are indistinguishable. Those 3 hydrogens on that methyl group are pretty much the same as those 3 hydrogens, same as those 3 hydrogens. So there's a total of 9 hydrogens. Well, with the pink, we've got 3. Okay, if we move over to this other signal, this pink signal, that's being generated by these 3 hydrogens. Okay, so 9 compared to 3 is the same as 3 compared to 1, right? Well, that's that relative area that we have here. So you can see the integration also helps us identify which peak goes with which hydrogens. So this green peak, is associated with these 9 hydrogens. All right, and that is evident in part due to the relative area underneath the peaks. It's a 3-to-1 ratio. All right, so the integration of the area under the peak can be used to quantify the different kinds of hydrogens in a molecule. So each peak is integrated, and that gives you a relative amount of each type of hydrogen in the molecule that you're analyzing. Okay, that's the value of looking at the integrations. Okay, here's just another example. We've got the methyl groups. There's 3 there and 3 there, so that's a total of 6 from the methyl groups. Whereas on the ring itself, there's a hydrogen at each one of these positions. So that's, a total of 4. Okay, so there's 6 hydrogens on the methyl groups, and there's 4 hydrogens on the ring itself. And so that's why the height of this integral versus the height of this integral line, okay, that would be like a 3 to 2 or 6 to 4, right? Because there's 6 of this type, the methyl protons, versus 4 on the ring. Okay, so that's a ratio of 3 to 2. The simplest ratio is 3 to 2, but if we make it match reality, it really is a 6 to 4. Okay, so again, those relative peak heights. Now, the other thing I want to point out about this is that the way the curves are shown here is different than they were in the previous slide. In the previous slide, if you don't mind, I'll draw this the way it was in the previous slide so you can see the difference. So it just had the curve, and then it just kept the line going, and then just started the curve and went from there. But you'll see it both ways in NMR spectra. Sometimes, they'll kind of split out this middle part of the line and then drop it down like they did here. You see it both ways. But you always just measure from the top to the bottom and just take the difference. That's what matters, is that difference between the top of the curve and the bottom of the curve. That's the integration. All right, so that's integration. So more detail about the peak splitting that we want to go over. And this is weird, but it is very powerful. So what happens is a peak can get split. by neighboring hydrogens. So we call that a multiplet. The multiplet is the absorption of a proton that splits into multiple peaks. So it splits into multiple peaks. And we even get more detailed about it. We give each splitting pattern a name. So if it is one nice looking single peak, we call that a singlet. And what that means is the hydrogen generating that peak has no hydrogens on its neighbors. Okay? If that peak gets split into two peaks of equal height, we call that a doublet. And what that means is that the hydrogen generating that peak has a carbon with one hydrogen on it, and it splits it into a doublet. And so why is it one hydrogen splitting it into a doublet? Well, that's where we get to the next formula, which we call the N+1 rule. So let me bring that up on our notes here. The N+1 rule. Okay? That rule says that a hydrogen generating a peak splits into N+1 peaks, where N is the number of equivalent neighboring hydrogens. Okay? N is the number of equivalent neighboring hydrogens. Okay. Now, again, what do we mean by equivalent? Well, we mean they have the same chemical environment. So chemically equivalent protons do not show spin-spin splitting. Okay. So we're going to do two examples. And again, the color coding is really helpful here. So the blue hydrogens, CH3, are represented by this blue peak here. Now, a lot of times the chart itself, it's not real obvious what the splitting pattern is, so you may have to zoom in, which is what they've done here. So this blue peak, we zoom in and we can see that it is a triplet. It's been split into three peaks, a triplet. Okay? So what that means is the hydrogens that are generating this blue peak, these hydrogens right here in the methyl group, CH3, okay, it's been split into a triplet. So that means that those hydrogens have a neighbor with two hydrogens on it. Because remember, the peaks split into N+1, the number of neighboring hydrogens plus 1. So the number of neighboring hydrogens here must be 2, because 2 plus 1 is 3. It splits into a triplet. And that's what we can see. These hydrogens are next to a carbon that's connected to 2 hydrogens. Okay? Okay, so now let's look at the CH2. Okay, so it's color-coded with pink. So here's the signal generated by those CH2 hydrogens. Now again, if you zoom in, you see that it's a quartet. Okay, so what that means is the hydrogens generating the signal are next to a carbon with N+1. So since this is 4, N+1 equals 4, so N must equal to 3. And that's what we see. So these two hydrogens that are generating this peak have a neighbor with 3 hydrogens on them. Okay. And if you need further proof of that, you go to the integration. So this first peak at 1.68, it would generate a relative peak area of 1.5 to 1 versus the peak at 3.42. Now remember, we can just multiply these times a factor if we want to, and it might make more sense if we do. So if we just multiply that times 2, then we get 3 hydrogens to 2 hydrogens. Okay, and that's what we said. So this stands for 3 hydrogens. Okay, and this stands for 2 hydrogens based on the integration. So here's just another example. So once again, what we have here is 2 types of hydrogens. The blue they're equivalent. Okay, the methyl group over here chemically is equivalent to the methyl group on the right. The left methyl is equivalent to the right methyl group. So that's a total of 6 hydrogens, and that's what it integrates at. So this peak at 1.71, this blue peak, integrates it as 6, and that matches what we expect. All right, so they are next to a carbon, whichever one you reference, whether you're talking about this carbon on the left, it's next to a carbon with 1 hydrogen on it, or if you look at the carbon on the right, it's next to a carbon with 1 hydrogen on it. So N+1 would be 2. 1 hydrogen plus 1 is 2, and so it does split into a doublet. You can see it splits into a doublet, okay? Because its neighbor has 1 hydrogen, N+1 is 2, splits into a doublet, okay? So now let's talk about the pink hydrogen. So first of all, recognize again that it integrates as a 1. So the height here is 1. This height here is 6. So it represents 1 hydrogen. And the number of hydrogen on its neighbor is 6 total. You got 3 on the left, you got 3 on the right, for a total of 6. So it should split into n plus 1. It should split into 7 peaks, and it does. 1, 2, 3, 4, 5, 6, 7. Now the first peak and the 7th peak are really small, but they're there, and it fits that pattern in terms of the peak height for each contributor. Okay, so we got a septet and a doublet. So that matches the structural features that we would expect for a compound like this. So now let's just do an example here where we're going to propose a structure. What we have is we have the chemical formula C4H10O, and we have this NMR spectrum right here. And so just with those two pieces of information, we can come up with the structure of this compound. All right, so let's start talking about it, and then we'll put all of the details into our notes in just a second. Okay, so first of all, I want you to recognize that what we've got is a total of 10 hydrogens here. So these two peaks are caused by 10 hydrogens. So right now, I'm accounting for 1.5 plus 1, so I'm only accounting for 2.5 hydrogens, because this says that the peak at 1.22 is caused by 1.5 hydrogens, which of course is not possible. So we know already that we got to at least multiply by 2, because you can't have a fraction of a hydrogen in a compound. So 1.5 times 2 is 3, and 1 times 2 is 2, okay? But that doesn't total 10. I need it to total 10. Well, what if I multiply by, it just totals 5. 3 plus 2 is 5. Well, what if I multiply it by 4? So 4 times 1.5 is 6. 4 times 1 is 4, and that does give us 10, okay? So this peak right here, it integrates, this is caused by 6 hydrogens. And this peak right here is caused by 4 hydrogens. The peak at 3.49 is caused by 4 hydrogens. The peak at 1.22 is caused by 6 hydrogens. Now, what else do we want to point out? Well, let's point out that we already talked about the integration. So the other thing I want to say is that, this peak is a little further downfield. So maybe that's near an electronegative atom. And we know what that atom is because it's given to us in the formula. It's oxygen. So whatever hydrogens are generating this peak at 3.49, I'm guessing that they are close to this oxygen, because that's why they are further downfield. Okay. Now let's think about the splitting pattern. So this is a quartet, 1, 2, 3, 4. So that means that it has 3 H's on the neighbor. Right? This right here is a triplet, 1, 2, 3. So that means that there's 2 hydrogens on the neighbor. And we saw this pattern in the previous example, one of the previous examples. And I hope that with experience, you just start to see some of these patterns. Whenever you've got a quartet next to a triplet, what that typically means is it's a CH2, CH3. It's an ethyl group, because remember, as we said, the proton NMR signal generated by these 2 hydrogens is going to be a quartet, because it's next to a carbon with 3 hydrogens. Boom, there's your quartet. And the signal generated by this methyl group is going to be a triplet, because it's next to a carbon with 2 hydrogens on it. N plus 1 equals 3. So the signal generated by that methyl group is going to be a triplet. Boom, that's what we have here. We've got a triplet. Okay. And so now, as I said, the other thing that we know about the signal that's being generated by the CH2 is that it's near an oxygen. So let's just go ahead and slap our oxygen there. Okay. All right. Well, right now we've only got 5 hydrogens accounted, because 3 plus 2 is 5. I need 10. Well, whatever is the other hydrogens are doing, they're generating signals the same as these sets of hydrogens. They must be chemically equivalent. So it must be just the same thing on the other side. So I got a CH2 and a CH3. Okay. So what's generating this NMR is diethyl ether. Okay. Because now this methyl group is equivalent with this methyl group. So that's 6 hydrogens giving us this signal. This CH2 group is equivalent to this CH2 group. Okay. You see that this CH2 group is the same chemically as this CH2 group. So that means that there's 4 hydrogens generating that signal. Okay, so that's the sort of process, the thought process that you go through to use an NMR to come up with the structure. Okay, and if you do move on to organic 2, then you'll do a lot more of this. The purpose today is just to introduce you to this particular skill set that you need to develop in organic 2. So things we already talked about, let's just start filling in blanks. The spectrum shows two signals. So there's two types of hydrogens in this compound. Okay, so the spectrum shows two signals corresponding to two types of hydrogen, and they have a ratio of 1.5 to 1. But we know that we can't have a fraction of a hydrogen in a compound, so it has to be at least 3 to 2. Okay? And furthermore, we know from the formula, we were given the empirical formula, C4H10, or the molecular formula, sorry, C4H10O. So we need 10 hydrogens. Well, 3 and 2 is 5, so if I just double that, it becomes 6 and 4. And so now we know that the unknown contains 10 hydrogens, 6 are of one type, and 4 are the other type. Because we only have two signals, so we can only have two types of hydrogens. So 6 are of one type, and 4 of the other type. Okay? And again, thinking about what we know about chemical shift, but one thing that we know is that if it's a saturated, if it's a hydrogen on a saturated sp3 carbon, it's going to give us signals that are upfield, near 0, near 1. So that peak at 1.22, that's from an sp3. Those are from hydrogens on sp3 carbon. And then the peak that's further downfield at 3.49, that must be from hydrogens that are on carbons adjacent to an electronegative atom, and we know what that atom is. In this case, it's oxygen because it's in the formula. Okay, so the downfield signal at 3.49, that's from protons on carbons adjacent to an electronegative atom, in this case, oxygen. Okay, so there's a typo here. You can fix it in your handout. It should say 1.22. I'm not sure why it says 1.23. But that's a triplet. So that indicates we've got two neighboring hydrogens. So the signal at 1.22 is a triplet, indicating two neighboring hydrogens. And the signal at 3.49 is a quartet, indicating three neighboring hydrogens. So we put all that together, and we say that this is characteristic of an ethyl group, the CH2CH3, that ethyl alkyl substituent kind of group. CH2CH3. All right, so now, taking into account the entire formula, we can say then that the compound is diethyl ether, CH3CH2O, CH2CH3. All right, so now we want to talk about, we got to muddy the waters a little bit, but don't worry, I won't expect you to know too much about this. This is, again, just we're just scratching the surface today, but there are a couple things that I need to point out to you that do complicate the situation. So first of all, if you have overlapping peaks, it gets messy. It's hard to say whether it's a doublet or a quartet or a septet. It just gets, really messy. So a lot of times we'll just simplify the classification and we'll just call it a multiplet. We won't dare to try to categorize it as a like I said, a sextet or a septet. We'll just say, hey, that's a multiplet. It's got lots of little peaks in it. And so you can see that with this example of the benzene, this is toluene. And so the hydrogens that are on the benzene ring, they form this peak right here. And if you tried to really figure out whether that's, how many individual peaks are in there, that's hard to do. And the reason why is because in a benzene ring, you get splitting from hydrogens on the other side of the benzene ring. So like, for example, this hydrogen right here is split by the hydrogen in the meta position. It's split by the hydrogen in the para and also in the ortho position. So there's different splitting patterns based on, the relative position on the benzene ring. So that gets very complicated. And it's beyond the scope of this course. We don't really need to learn that today. Okay, so some hydrogens in a molecule just accidentally overlap. So if you have a splitting by two or more non-equivalent kinds of protons, it just gets more complicated. And so what I'll do is I'll focus in on this blue. Look at this blue signal right here. So if you zoom in, you can see that it's 4 peaks, but it's not a quartet because the heights don't match the pattern for a quartet. A quartet, the two spikes on the ends are smaller than the two spikes in the middle. Okay, so this is not a quartet. What this is, to give you the proper name for it, is this is a doublet of doublets. So it's this blue hydrogen is generating this signal. So the reason why it's a doublet of doublets is because one neighboring carbon has one hydrogen on it, so that gets you a doublet. But then the other neighbor also has one hydrogen on it, so that gets you a doublet. And they are chemically distinct. So this hydrogen that's green is chemically different than this hydrogen that's pink. So they each split the blue hydrogen on their own. And so this splits it into a doublet, and this splits it into a doublet. And so what you get is a doublet of doublets. And so it looks like, four equally sized spikes.
Okay, so one other situation that we want to talk about with regard to peak splitting is when there is no peak splitting. And that happens in a couple situations. First of all, whenever there's a hydrogen attached to oxygen in alcohols, or if we have them attached to nitrogen in amines. What happens in that situation is instead of peak splitting, you get peak broadening. Okay? So an example of that is this NMR spectrum of ethanol, which we've already talked about how this pattern of a quartet and a triplet, that tells us that we have a CH2 and a CH3. And then this right here, because it's right at 0, we know is TMS. And so this peak right here is for the hydrogen that's on the alcohol functional group. And notice that it's broadened. It doesn't display any splitting at all. So this is just another important attribute of hydrogens in NMR spectra.
Okay, so to wrap things up for this lecture part, I want to go through one more example where we're going to look at a compound and we're going to assign the peaks in the NMR to each of the hydrogen types in this compound. So the first thing we got to do here, as we're in this guided process here, is we need to figure out how many types of hydrogen there are in this molecule. All right, so let's think about that. So we're just looking for the different types of hydrogens that are in this molecule. So we already said that we're just going to count all of these hydrogens in the benzene ring. We're going to lump those together. So let's just call those hydrogen type A. So I'll label all those with A's. HA. So these are all hydrogens of type A. And there's 5 of them. Okay. All right, so now let's just move down the line. So right here, these 2 hydrogens on this carbon, they're unique because, they're different than HA. And there's some hydrogens over here, and they're going to be different than those because they're just kind of in a unique chemical environment. On the left, they've got this benzene ring, and on the right, they've got this carbonyl. So let's label those hydrogen type B. Now, similarly, this CH2 group right here, that's a unique type of hydrogen because on its left side, it's got a carbonyl, and on its right side, it's got a methyl group. So that's a unique type of hydrogen. So we'll label that as hydrogen C. And then finally, these hydrogens over here in this methyl group, they're unique. So we'll just call those hydrogens D, HD, HD, HD. Okay, so what that means is there are 4 types of hydrogens in this compound. And so essentially what that means is we're going to expect to see 4 peaks in the proton NMR spectrum. Okay, that's what that means. When we decide how many types of hydrogens there are, that's how many peaks we expect to see in the spectrum. Okay, so now let's just go ahead and try and predict the approximate positions we would expect each of these peaks to show up in the spectrum. Okay, so we're just going to talk about each one of these. Okay, so hydrogen type A. Well, what is it? It's on a benzene ring. Well, I expect that hydrogens on a benzene ring are going to go from that range of about 6.5 to 8. So I expect that to be, in the range of, we'll get to that in just a second, but it should be in that range of 6.5 to 8. Okay, and hydrogens type B, right here, okay, well, those are on a saturated carbon, right? It's an sp3 carbon. It's got 4 single bonds. But the thing about it is, it's near 2 electron withdrawing groups. This carbonyl and this benzene ring are going to both act like electron withdrawing groups. So these are going to be a little bit downfield, around 1.5, but in parentheses, I'm just going to say downfield. Because that's the key thing, is that the peak generated by hydrogen type B should be shifted downfield a little bit because of these electron withdrawing groups, the carbonyl and the benzene ring. Okay, so what about C? Well, again, that's on a sp3 carbon, and it's next to 1 electron withdrawing group, but not 2. So the H-type hydrogen type B is sandwiched between 2 electron withdrawing groups. Hydrogen type C is only near 1, electron withdrawing group. So that's going to be, I don't know, maybe around 1.5, but we're going to say it's upfield of B, right? Because it's just not experiencing quite as much de-shielding as the hydrogens type B are. Okay, and then finally D, these fit nicely into this category of this saturated uh, hydrogens on saturated sp3 carbons. So let's just say that that's probably going to be around, anywhere from 0 to 1. Okay, I would expect to see those anywhere from 0 to 1. Okay, so A, 6.5 to 8, that's the aromatic region. B, I say anywhere from 2 to 5, but that's again because I'm just accounting for the de-shielding from those electron withdrawing groups. C, somewhere around 2.5. Again, the big thing to note there is that it's going to be upfield of hydrogen type B. And then D is going to be anywhere from 0. I said 0 to 1, 0 to 1.5. That's fine. Okay, so now let's think about the splitting pattern that we would expect from each hydrogen type now. Okay, so the hydrogen type A, remember we said that that's one of those complex situations. Those are hydrogens on a benzene ring. So I won't be able to give it a nice numeric value. It's just going to be, we're going to consider it a multiplet. Okay, and I'll just go ahead and show you all of them. But B, if you look at hydrogen type B, I'm just going to say it's going to be a singlet because its neighbors don't have any hydrogens on it. So these hydrogens, their neighbors have no hydrogens. That carbon has no hydrogens. That carbon has no hydrogens. So that's why I've said it's expected to be a singlet. Hydrogen type C. Well, we've seen that before. This is a CH2 group, which is next to a CH3 group. So its neighbor has 3 hydrogens. So 3 plus 1 is 4. So I expect hydrogen type C to give us a quartet. And then hydrogen type D, we've seen this before, has a neighbor with 2 hydrogens on it. So n plus 1 is 3. So I expect it to be a triplet. We already said we expect, if you look at the actual spectrum, like I said, sometimes it's hard to tell unless you zoom in. So I'm just giving you what these are. So this peak somewhere between 7 and 7.5, we're just going to classify that as a multiplet. This peak around 3.6, we're going to say that's a singlet. The peak around 2.5 is a quartet, and the peak around 1 is a triplet. And then if you look at the integrations, the relative integrations, they would account for 5 hydrogens for the multiplet, 2 hydrogens for the singlet, 2 hydrogens for the quartet, and 3 hydrogens for the triplet. Okay, so now we should be able to say which peak corresponds to which hydrogen type. So, the aromatic hydrogens, A is for this peak. Right here is the singlet, B. This one is the CH2 quartet, C. And then this one is the triplet, CH3D. Okay. Now, not every time will it perfectly go from left to right like it did in this example. I'm just, trying to teach you the process with this example.